Good morning, students. In the last class only we discussed about the decays. So we have three types of decay. Right. So in that first one is alpha decay, beta decay, and gamma decay. Right. So here in the alpha decay, the emission of the alpha particle, that is the nucleus of the helium atom. Right. So in the beta decay, the emission of the electrons or protons from electrons or positrons from the nucleus. So that one we call as beta decay, and gamma decay here. So high energy photons are released from the nucleus of the atom. So that one we call as gamma decay. Right. So here we have three types of decay. So we will discuss one by one. So starts with alpha decay. Right. So what is alpha decay? Right. So the emission of the alpha particle from the nucleus of the atom. So that process is called as alpha decay. That is the process of emission of the alpha particle from the nucleus of an atom. So that process is called as alpha decay. Right. So the emission of the process of emission of alpha particle from the nucleus of the atom right. So that process we call as alpha decay, right. So what is alpha decay? Means the process of emission of the alpha particle. So what are alpha particles? So alpha particles are the nucleus of helium atom, right. So what are alpha particles? So alpha particles are the nucleus of the helium atom. So the helium atom is He4, that is mass number is 4 and its atomic number is 2, right. So in alpha decay, if we consider the element X, it has mass number A and it has atomic number Z, right. So from this element, the nucleus of this atom, while taking the alpha decay, right. So as we said, it emits the helium atom nucleus, that is He2 4, right. So here this decaying element or decaying atom we call as parent atom or parent nuclei, right. So this decaying element, that is decaying nucleus, we call as parent atom or we call as parent nucleus, right. So when this nucleus undergoes decay, it emits the helium nucleus, right. That is He4, that is mass number is 4 and its atomic number is 2, right. So here after it undergoes decay, then here we get the nucleus which is formed after the decay. That nucleus having the mass number which is less than 4 to that of the original element, that is original nucleus having mass number A. Here the mass number is decreases by 4 and also the atomic number is also decreases by 2, right. So the nucleus which is formed in such a manner after that of the decaying of the parent atom, then that atom we call as daughter element or daughter atom, or we call this one as daughter. here also in case of atom, nucleus, and here we have daughter nucleus, right? So in alpha decay, so this one is the general form of the alpha decay, right? So in this general form, so where X is the parent nuclei, where A is the mass number and Z is the atomic number and X is the chemical symbol of the species of any element, right? So after this element undergoes alpha decay, so one element which is formed, so that element we call as daughter nucleus. So in this daughter nucleus, the mass number is decreases by 4 and the atomic number is decreases by 2. So here this particle He42, so this one we call as alpha particle, right? So this is the general form of the alpha decay, right? So here where A is the mass number, Z is the atomic number. So mass number decreases by 4 and the atomic number is decreases by 2, right? So if we take one example, so uranium 238 and its atomic number is 92. When it undergoes alpha decay, so we get thorium 234 and here it is 90 plus He4, right? So if you observe here the mass number A is 238, so it is decreases by 4. That means here the mass number is 234. That is 238 minus 4, we get 234, and atomic number is 92 and it is decreases by 2 and it becomes 90, right? So here the element is uranium. So here we get the after decay, the nucleus which is formed, so that element is the thorium. It has the atomic number 90, right? So in periodic table, when any element undergoes alpha decay, right? So if we consider this one is periodic table in a row, here we have number of elements, right? So for example, here we considered X here. That means the parent atom or parent nuclei present somewhere here. It has mass number A and it has atomic number Z. After it undergoes decay, the daughter nucleus which is formed, so it shifts to the two numbers left into that of the periodic table, right? So here we get Y, that is A minus 4, that is Z minus 2. That means it present in the 2. This one is the first and this one is the second, right? So in the second row, that is shift is from here to here. That means it shifts from 1 and here it is 2 because it is decreases by the atomic number 2. If the uranium is present here, then the daughter nuclei thorium is present. 2 rows left to that of the parent nuclei, right? So here this one is the parent nuclei and 2 rows left to that of the parent nuclei. The thorium is present in the periodic table, right? So this will be given in here uranium. It shifts to that of the nucleus which is present, the new element which is thorium, right? So if we take one more example, that is plutonium, right? So its mass number is 242.94, right? So when it undergoes decay, we get uranium 238 and atomic number is 92 and we get the alpha particle, right? So here we have the plutonium 242. So 242 minus 4, we get 238, right? So plutonium, we have atomic number 94 and here in the uranium we get the atomic number 2. That means it decreases by 2. That means if the plutonium is present here, then the daughter element is the uranium. It shifts to the 2 left to that in the periodic table, right? So understand this one. So here we have the plutonium. So 2 left to that is uranium If we take the uranium nucleus, then it two left to that one is the thorium, right? So like this, if we consider here thorium, we get one more element somewhere here after we get the decay, right? So this is about the alpha decay, right? So when this alpha decay is takes place, right? So when the alpha decay is takes place, that means spontaneous emission of the helium nucleus is takes place only when the mass of the products of the daughter element and the helium atom, that is helium nucleus, is less than the original mass of the nucleus, then only the alpha particles are emitted from the nucleus, right? When the reason for the alpha decay is when it will take alpha emission, that is alpha decay. So this example is very important. So two times they asked, this year also they asked this for 1 marks in 2020, and in the last year also they asked this example for 1 marks, right? So write the radioactive, that is alpha decay for the uranium 238. Then we need to write this relation, right? So here we need to write alpha decay. Right, so this one is very important. You need to remember these two examples. So this year and previous year, back to back, they asked for 1 marks. Write the alpha decay relation for the uranium 238. Right. So this is important for 1 mark. Right. So the reason why the alpha decay takes place is so these two we call as products. Right, so as already you know this one in chemistry, right, reactants and products. So here we are getting the products. So this one we call as decaying nucleus, right? So the reason why the emission of the alpha particle takes place means the mass of the products products of the elements is less than the mass, that is initial mass of the nucleus. So that's why the alpha decay is takes place. That is the reason for the emission of the alpha particle, right? So the reason is that the size or mass of the products of daughter element products, that is daughter element and alpha particle is less than the mass of the initial nucleus, right? So for this reason only the emission of the alpha particle is takes place. That means the alpha decay is that takes place only because of the reason, that is the mass of the products. That means products means daughter element plus alpha particle. So the combined mass of these two particles should be less than the mass of the original mass, that is initial mass of the nucleus, then only the emission of the alpha particle takes place, right? So this is also important. They may ask for 1 mark, that is the reason they are asking, right? So next is from Einstein's mass energy relation and conservation of energy. So from E is equals to mc square and conservation of energy, we have disintegration energy, or we call that one as Q value of nuclear reaction, right? So what is disintegration energy or Q value of the nuclear energy, right? So that is the Q value of the nuclear energy is the difference in the mass energy of the initial mass to that of the product mass, right? Product mass is nothing but the daughter element's mass and alpha particle mass energy, right? So from this relation we are going to define the disintegration energy. So what is disintegration energy or Q value of a nuclear reaction means? It is the difference in initial mass energy to the total mass of the products, total mass of the products total mass energy of the decay products, right? So here we know the reason why the alpha particle is emitting. That means the mass of the products is less than the mass of the initial nucleus, right? So that means here we have the uranium nucleus. So this mass is greater than the decay products. Decay products nothing but here we have daughter element along with the alpha particle, right? So combined these masses is less than that of the initial mass, right? So from the relation Einstein's mass energy relation we have E is equals to mc square. So by using this one we are going to defining the relation, that is disintegration energy or Q value of the nuclear reaction. That means here we have mass, that means here we have the mass difference, right? So if there is mass difference then automatically we have energy difference because we directly relates with energy and mass, right? So that energy we call as disintegration energy, that is difference in the initial mass energy to that of the total mass energy of the decay products. That means the mass energy of the parent nuclei minus the mass energy of the decay products. That value is given by the disintegration energy. So that is denoted by Q, right? So if we write the general form for the disintegration energy, right? So here we have for alpha decay, we have the general formula X, A, Z. This one is the parent nuclei. When it undergoes alpha decay, we are getting daughter nuclei, that is Y, A minus 4, Z minus 2 plus He4 2. Right? Now we are writing the Q value of the nuclear reaction. For that Q, that is equals to what we say here, it is the difference in the initial mass energy, that means mass of this parent nuclei, that means mx square, right? By using E is equals to mc square, here m is the mass of the parent nucleus, so that one is indicated by x, mass of the parent nucleus mx into c square, right? Minus, difference is nothing but minus, subtraction between those two values minus sum of the products of the daughter and to that of the alpha particle, right? That means sum of the masses. Here mass of the daughter is we taken my plus mass of the helium atom we taken He into c square, right? So this gives the mass of daughter nuclei and Mhe gives the mass of helium, that is alpha particle, into c square, right? So if you observe here in these two we have common term, that is c square, right? So that can be written as q is equals to mx minus, if we multiply inside, so plus into minus my minus into plus minus He. So here we are going to take on common, so that common is c square, right? So this is the relation for the disintegration energy, right? So disintegration energy or Q value of a nuclear reaction is the difference in the mass of, that is difference in the initial mass energy to that of the total mass of the decay products, right? So this is the total mass of the decay products. My is the mass of the daughter nuclei and Mh is the mass of the alpha particle into c square. So this is, we are writing by the equation E is equals to mc square, right? So here if I write mx mass of parent nuclei, if they ask for one mass, write the relation for the disintegration energy, we need to write q is equals to mx minus my minus mhe into c square. Then we need to define those terms. So mx is the mass of the parent nuclei, my is the mass of daughter nuclei, and mhe is the mass of alpha particle, right? So and another one is c is speed of light in vacuum, right? So this is about the alpha decay. So in alpha decay we have the definition: the process of emission of the alpha particle from the nucleus of an element or atom. So that process we call as alpha decay. So in alpha decay, the daughter nuclei which is formed, that nuclei is the mass number is less by the 4 and the atomic number is decreases by 2. Then the alpha particle is emitted. The reason for the emission of the, that is spontaneous emission of the alpha particle, is the mass of the product is less than that of the original nuclei, right? So next is disintegration energy or Q value of the nuclear reaction. So here the disintegration energy is defined as the difference in the initial mass energy to that of the total mass energy of the decay products, right? So for that we have the relation Q is equals to mx minus my minus he into c square, right? So here the example is very important in all the decays, right? So this is about the alpha decay. Next we move on to the next one, that is beta decay. next one is beta decay. So beta decay is beta symbol. Here it is decay, right? So in beta decay, the process of emission of the electrons and positrons from the nucleus of the atom, so that process we call as beta decay. That is the process of emission of electrons or positrons from the nucleus of an atom, right? So that process we call as beta decay, right? So here one is electrons and another one is positron, right? So here in beta decay, either it may be emit electrons or it may be emit positrons. So that's why here we have two types. In beta decay we have two types. So one is beta minus decay, right? So another one is beta plus decay, right? So in beta minus decay, the emission of the electrons takes place. So in beta decay, the emission of the electrons takes place. In beta plus decay, the emission of the positrons takes place. Right? In beta plus decay, emission of the positron, right? So if we write the general form, so here X, A, Z. So this one is the parent nuclei. When it undergoes beta decay, here mass number, that is Z plus 1, plus the emission of the electron 0, and here it is minus 1. So along with this electron, one more we are getting new bond, right? So this one is the electron. So along with electron, we have one more particle. So that one is anti-neutrino, right? So here the daughter element which is formed after the beta decay, it is lies one next to that of the parent nuclei in the periodic table, right? So here we have periodic table means, so here we have the parent nuclei X, then one next to that of the parent nuclei, right? So here we are getting the daughter nuclei, that is daughter element, right? So here we have X1 next to right of the periodic table, we are getting the daughter nuclei, because here we have Z. For example, here we have Z, X is equals to, that is parent nuclei having the atomic number 90, then the daughter element we are getting 91. That means it shifts one next to that of the parent nuclei in the periodic table, because here we have Z plus 1, that is 90 plus 1, we are getting 91, right? So this is the general form of the beta decay. Now we will take few examples for the beta decay. For that we have phosphorus 32, 15. When it undergoes beta decay, we get sulfur, or mass number remains same as it is 32, and its atomic number is increases by 1 and it becomes 16, plus the emission of the electron along with anti-neutrino, right? So this one is the beta decay, right? So one more example is lithium. Here it is 8 and here it is So as it undergoes beta decay, lithium becomes beryllium, mass number 8 and 3 becomes 4, and here it is electron plus anti-neutrino, right? So these are the two examples for the beta minus decay, right? So next, in beta plus decay, here if we consider this one as the parent nuclei having mass number A and atomic number Z, as it undergoes beta plus decay, the daughter nuclei which is formed, so here also the mass number remains same as it is and its atomic number is decreases by 1, that is Z minus 1, and here we are getting 0 plus 1 plus nu, right? So this element we call as positron, and here this one we call as neutrino. So as similar here in the periodic table, here we have X, that is parent nuclei, then the daughter nuclei will lie one next to, that is one minus, that is left to that of the parent nuclei. So here we get in the daughter nuclei, right? So X is the parent and Y is the daughter. Here we getting one next to right in the periodic table, here one left to that in the periodic table, because here Z minus 1. Here the X value is 90, then the daughter value will have 89, because 90 minus 1 is 89, right? So that's why it falls one next to that in the periodic table, that is left, and here we getting in right, right? So here if you take example of the beta decay, beta plus decay, and here we have beta minus decay. Sodium in 82211, right? So as it undergoes beta decay, we are getting neon in E, mass number remains same and it becomes 10 plus E 0 plus 1 plus E, right? So one more example is fluorine 18 and here it is 9, as it undergoes beta plus decay. So fluorine next to that one is oxygen, mass number 18, here it becomes 8 plus E01 plus nu, that one is the neutrino, right? So here what are positron? So positron having the same mass that of the electron, but it is opposite charge. If electron is negatively charged, then positron is positively charged. The masses of the electron and masses of the positron both are same. That is masses of the electron that is equals to masses of the positron. Both are same, but it has opposite charge, right? So that is the difference between the electron and positron, right? So here electron is negatively charged, positron is positively charged. Both the masses have same. Positron's mass is same as that of the mass of the electron, right? So here one more particle we are getting here, that one is the neutrino. So what are neutrino? So neutrino are the elementary particles, so which are neutrino, that is nu. So neutrino are the elementary particles, so those particles which does not have any mass, that means it has massless right? And it does not have any charge. So that means it has no charge, that is chargeless, but it only had spin. It has spin, right? So what are neutrino? Neutrino are the elementary particles which doesn't have any mass and charge. It has only the spin, right? So that particle we call as neutrino. So then what are anti-neutrino? So anti-neutrino is also the elementary particle. So it has also, that means it does not have any charge and any mass, but its spin is opposite to that of the neutrino, right? So hence for that reason we are writing bar symbol on the neutrino, that is nu bar, and here we have only the nu, right? So that is the difference between neutrino and anti-neutrino, right? So here it mainly difference is the spin, right? So if the neutrino has spin in one direction, then anti-neutrino is opposite to that of the neutrino, right? So next, here, if you observe here, in beta plus decay, the emission of the electron takes place. As already said, this one is the parent nuclei. As we already know, so the nucleus is only consist of protons and neutrons. So this does not contains any electrons inside the nucleus, right? So there is no electrons inside the nucleus. Then how it will emits the electron? So this nucleus, how it emits the electron, right? So as already says in the last class, neutron when it comes outside the nucleus, it is unstable. Neutron is unstable when it is comes outside the nucleus, right? So this neutron decays into protons or electrons, or it converted into anti-neutrinos, right? So this neutron is only stable when it is present inside the nucleus, right? So this is the nucleus. The neutron is only stable when it is present inside the nucleus. When once it comes outside from the nucleus, so this neutron is unstable, right? So for that reason, this neutron is decays into protons, or it may be decays into electrons, or it may be decay into antineutrino particles, right? So hence when it comes outside the nucleus, it decays into protons, electrons or antineutrinos. Then from that the electrons are emitted, right? So this is the reason why the parent nuclei emits the electron. As this nuclei does not consist of any electrons, the reason is when the neutron comes outside of the nucleus, it becomes unstable. So this neutron undergoes the decay into proton. That time the electrons are emitted, right? So for that reason, the emission of the electrons takes place, right? So once they ask this one for 1 mark, right? That is, electrons does not pre-exist inside the nucleus. The reason, that is, electrons does not pre-exist inside the nucleus. It is formed formed due to conversion of neutron into proton and proton into neutron, right? So here neutron is converting into proton plus the emission of the electron plus along with one anti-neutrino, right? So this is when neutron is converting into the proton. As I already says, in the nucleus we have both protons and neutrons. When neutron is converting into the proton, the emission of the electron is takes place. So similarly here, proton is converting into neutron, that is proton undergoes the neutron, then here the emission of the positron along with neutrino, right? So this is takes place in beta minus decay, and this will take place in beta plus decay. They ask the reason why the neutron is converting into the proton. So this is the reason why the nucleus emits the electron, right? As electron does not pre-exist inside the nucleus, but also it emits the electron, that is due to the conversion of neutron into proton and proton into neutron. So that time we are getting emission of the electron and emission of the positron, right? So the next topic is, so this is asked for 1 marks in 2018. Why neutron is converted into proton and why proton is converted into neutron, right? So the reason, because the mass of the proton is lesser than that of the mass of the neutron, right? This is only possible inside the nucleus. This is only possible inside the nucleus because mass of the proton is lesser than that of neutron, right? So here we have two explanations for two reasons, right? So one, why the electrons are emitted if it does not consist inside the nucleus. Inside the nucleus we don't have any electrons, but also while the beta decay undergoing, the electrons are emitting. The reason, because it is converting neutrons into protons, that is conversion of protons into neutrons and neutrons into protons. So that time the emission of the electrons takes place, right? So from proton to neutron, the emission of the positron takes place. From neutron to proton, the emission of the electrons takes place, right? So next reason is why the neutron and positron gets decay. For that, the reason is it takes place only inside the nucleus because the mass of the proton is less than the mass of the neutron, right? So if we write mass of the proton which is less than the mass of the neutron, because of this reason only the neutron and proton decay takes place, right? So this is asked for 1 marks in 2018. Why? The neutron undergoes decay in the inside the nucleus. The reason, because the mass of the proton is less than the mass of the neutron, right? So this is about the beta decay, right? So from this topic there will be no long answer, that is in alpha decay or beta decay or gamma decay. So we have to more concentrated on 1 marks question, right? So once they asked this question in 2018, right? So this is about the beta decay. So in beta decay, the emission of the electrons and positrons takes place. So if it emits the electron, then that one we call as beta minus decay. When it takes place positron, then that decay we call as beta plus decay. So in the beta decay, the mass number remains same, but the atomic number is decreases by 1 and increases by 1. So decreases by 1 in beta plus decay and increases by 1 in beta minus decay. So the next one is gamma decay. Right? So in gamma decay, whenever the nuclei which undergoes alpha decay or beta decay, then it goes to the excited state. So that time when it comes back to its original state by emitting the photons. So photons is nothing but the energy packet. So that rays we call as gamma decay. By emitting the gamma radiations, that is from excited state to ground state. So that radiation we call as gamma radiation and the decay we call as gamma decay. So here in gamma decay, the mass number and the atomic number remains same as that of the parent nuclei, right? So in gamma decay, whenever whenever the nuclei of atom undergoes alpha decay or beta decay, it will be in excited, it will be in excited state. It comes back to ground state by emitting gamma radiations. So this decay we call as gamma decay, right? So if we write in general, when AXZ, that is the parent nuclei, as it undergoes alpha decay or beta decay, then it goes to excited state, right? So as mass number and atomic number remains same, then the excited state is indicated by these stars, right? So along with this, gamma radiations are emitted. Right, so this one is the general form, right? So considering one example, that is cobalt 60 and it is 27, right? So when it undergoes beta minus decay, as it undergoes beta minus decay, beta minus decay, what happens? So atomic number is decreases by 1, so increases by 1, right? So here we getting in place of cobalt, here we getting nickel, that is mass number 60 and it becomes 28 plus here emission of the electron because it undergoes beta decay, right? So next plus 1 anti-neutrino. Now this is in the excited state. Now this nickel has to comes to ground state, then Li 60 Here it is 28. It undergoes gamma decay. Here Ni 60 and here it is 28 plus gamma radiations, right? So it emits the energy 1.17 mega electron volt. Again, next it comes to ground state I 60 and here it is 28. Then it comes to ground state Ni 60, 28 plus gamma radiation. Here also it emits 1.33 mega electron volt. Right? Z minus 1 plus electron plus anti-neutrino. Right? So this one is the example. For this example, you need to write all the three steps, and here we need to indicate the how much energy is releasing. As we already know in the electrons energy levels, right? So here also we have energy levels. So this one, and here we have in the nucleus also we have different energy levels. In electrons we have energy levels measured in terms of only in electron volts. So but in nucleus we have the energy levels in mega electron volt. That means it has higher energies compared to that of in the electrons, because mega is 10 to the power of 6 electron volt. So this is in electron and this is in nucleus. Energy levels in electrons is measured in electron volt, and in nucleus we are measuring in mega electron volt, right? So as all the energy levels similar as that of in the electrons, right? So considering here, we take on the example as cobalt 60 and it is 27, right? So this is first it undergoes beta minus decay, then here we get nickel in the excited state, that is 60 and here it is 28, right? So next it undergoes energy level from higher energy to lower energy. Then it emits the gamma radiations, right? So then here this state is Ni 60 and here it is 28. Again it comes to ground state. Here also it emits the radiation, that is gamma radiations, right? So this one is in the ground state. Here 60, 28, right? So here the energy of the gamma radiation is 1.17 mega electron volt, and here the energy of the gamma radiation 1.33 mega electron volt. As already says, the emission of the, in the last chapter in the atoms we discussed that the emission of the energy, right? So this is the nucleus and we have the electron orbit, right? When the electron is getting transition from higher energy state to lower energy state, that time it emits the energy. So similarly here also it transition from higher energy state to lower energy state, so that time it emits the energy. So that in the form of gamma radiation, that is highly penetrating radiation. So having the energy 1.17 mega electron volt. So further it transitions from first state to ground state. Then also here it emits the radiation. So having the energy E nu, that is E gamma, that is equals to 1.33 mega electron volts. Right? So this is about the gamma decay. So here in this, the definition and example is very important. Right? So in the next class, we will continue with the last topic, that is nuclear energy. In that we have two reactions, one is fission and another one is fusion. Right? Thank you.